Dalton's atomic theory, 1808. These are right out of your book. But first thing is he was kind of the first person to try to really define what an atom was. And he kind of came up with 4 different things. Elements are composed of extremely small particles called atoms. The next thing is all atoms of a given element are identical, having the same size, mass, and chemical properties. And second, the atoms of one element are different from the atoms of all other elements. Where he went wrong is this right here. Okay, all atoms of a given element are not identical. Why not? We have isotopes. Alright, stuff with the same atomic number but different mass number, so neutrons change. 3, compounds are composed of atoms of more than one element. In any compound, the ratio of the numbers of atoms of any 2 of the elements present is either an integer or a simple fraction. On the next slide, we're going to talk about this a little bit more detail. And then number 4, a chemical reaction involves only the separation, combination, or rearrangement of atoms. It does not result in their creation or destruction. Okay, and that is true of chemical reactions. So number 3, it really concerns these 2 kind of subsets of kind of definitions. So the law of definite proportions. Different samples of the same compound always contain its elements in the same proportion by mass. So if you are getting water every time, okay, H2O, anytime you have what we know as water, we have 2 parts hydrogen to 1 part oxygen. Okay, so if it's water, it is always this. Law of multiple proportions. If 2 elements can form more than one compound, the masses of one element that combined with a fixed mass of the other elements are in ratios of small whole numbers. Alright? So water is H2O2, but H and O can also combine to make hydrogen peroxide, which is H2O2. Alright? And in this case, really what the law of multiple proportions says, if things can combine in multiple ways, they always combine in ways that are whole numbers. Alright? So you'd never have H2O 2.5. Okay? If it's a 2.5, it's possible you might have something H4O9, but it's never going to be anything other than a whole number. Okay, so we had the atom kind of established in 1808, kind of right before or right after the turn of the century. J.J. Thomson was kind of working on a little bit of work done by Crookes, I believe was his name, but he kind of looked at the cathode ray tube and was able to see, basically measured the mass to charge ratio of an electron. I don't know how he did this, it's not important for our class, but kind of what he's noted for is we have a magnet here. Here's the negative sign right here of our magnet. Here's the positive sign. And really what happened was this cathode ray tube was kind of just a beam of electrons, and as you had the positive close to this beam, this would be deflected. Alright? So whatever this beam was made up of something that had a negative charge. Alright? And here's just some pictures of it. Here's a cathode ray tube. Here's your beam of kind of electrons or light given off kind of, it's actually a radioactive beam, and here's a little radioactive symbol. And then as he puts the magnet up, it gets deflected down. When he flips the magnet, it gets, or not deflected, I get deflected down. And when he puts the magnet this way, it gets kind of deflected up. Alright? Millikan was kind of the guy that kind of determined what the charge of an electron really was. Okay? And he kind of used stuff that, our last guy, Thomson had done to find out the mass of an electron. Alright? And again, Nobel Prize in Physics, and he determined the charge, or he figured out the charge of an electron. And then using Thomson's charge to mass ratio, knowing the charge in this ratio, he could determine the mass. Alright? Which is a really, 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 really small mass. Okay? Electrons don't take up much space, and they certainly don't have that much mass. We're going to look at these in your next vodcast. Alright? Alpha particles, beta particles, and gamma particles. These are types of radioactive particles that are given off, alright, in varying degrees of damage to humans. Alpha being the least harmful, betas being really harmful, and gammas, they move so quickly and we get hit with them. We're kind of protected by our planet, but we'll kind of talk about these a little more in depth in our next podcast. Alright, so Thomson's model of the atom looks something like this. It's often called the plum pudding model. Alright, he was an Englishman, and they like their plum pudding in England. So, plum pudding. When I say Thomson, I would like you to think of plum pudding. So, the plum pudding model. And essentially, all this inner part just was a positive charge, because this positive was spread throughout, and then we had just little specks of negative charge to balance this positive charge. Okay, so positive charge spread over the entire sphere, and just little bits of negative. I kind of like to call it the chocolate chip cookie dough model. You have the dough, which is positive, and then the chocolate chips themselves are your electrons. Rutherford then gets credit for the next really big discovery, and this was, notice this was actually before they found the mass of the electrons, all right? But he set up an alpha particle emitter, so he had some radioactive substance kind of in a lead casing, and these are giving off alpha particles, and here's a piece of gold foil, kind of like aluminum foil, and what he expected was, if the model that Thomson came up with, the plum pudding model, was true, everything should just go right through this gold foil. This is moving at an immense speed. It's not going to hit anything because there's nothing really hard enough to hit in the gold foil. So our particles are just going to go straight through the gold foil. And notice a lot of them did go straight through. Some got deflected a little bit. Here's a little bit of a deflection. Here's a little bit more deflection. Here's more deflection. And then some of them came right back at him. Stuff like this. Okay? So in order to make sense of this, he kind of came up with some other things. Atom's positive charge is concentrated in what's now the nucleus. Okay, so he's the guy that kind of came up with the nucleus of the atom. Proton has an opposite charge from an electron. Okay, so all the positives in the center. And then the mass of a proton is about 1,800 times more massive than that of an electron. All right, and you can see its magnitude of about 4 over here. All right, it's about 4 times 2. So Rutherford's model of the atom, we have protons and neutrons still we didn't know about. They were kind of the last things to be discovered. But his model of the atom is really the nuclear model. Alright, so nuclear model, and it did not have neutrons. I hate this slide, there's no neutrons, just protons for nuclear model. Alright, and this is really cool, this last little bit. If the Houston Astrodome is an atom, then the nucleus is a marble on the 50-yard line. You've probably never been to the Houston Astrodome, but if Chiefs Stadium, alright, was an atom, if there was a marble on the 50-yard line, you imagine the stadium going up above the ground as tall as it is wide, and below the ground, just a sphere around that marble. That's the size of your atom, and that's the marble. Okay, so all that positive stuff is crammed, packed into a really dense nucleus. Here's kind of the guys. Crookes, cathode ray tube, Thomson really gets credit for it. Millikan charged an electron, amassed an electron, and then Rutherford gold foil experiment with the nucleus. All right, and then Chadwick is the neutron, and really a lot of this stuff we're breezing through it. It doesn't seem to come up on the AP test all that often. And just kind of our look at stuff. Electrons negative charge, protons positive charge, neutrons no charge, therefore they are neutral. And then here's our masses again. Basically, a proton and neutron weigh about the same thing. All right, there's not much difference here, and they're about a magnitude of 4 times heavier than electrons. All right, atomic number, mass number, and isotopes. Atomic number is usually designated the capital letter Z, and it's always the number of protons in the nucleus. The mass number is designated by the capital letter A, and it is the number of protons and the number of neutrons. If we go back to our last slide, what are the two things that really have all the mass? They are the proton and the neutron. So if we want to know the mass number, we need to add up these two things that have the most mass, because the electrons are so unmassive, or light compared to protons and neutrons, they're not going to contribute to the mass number. Isotopes are atoms of the same element with different numbers of neutrons in their nuclei. Okay, so this is where Dalton was wrong. He said all atoms of an element are identical, but they are not, because of what we now know is isotopes. And here's what isotopic notation looks like. Okay, so X is your element, any element from the periodic table. Z is kind of redundant because it's the number of protons in the nucleus. So if we know the element symbol, we automatically know the protons. They're always written on a periodic table for us. So really just the A could possibly change depending on which specific isotope we're talking about. Here's the 3 isotopes of hydrogen. We have hydrogen without a neutron, okay, 0 neutrons, hydrogen with 1 neutron, hydrogen with 2 neutrons, and this is hydrogen, this is deuterium, and tritium. And again, we'll talk about this a little bit more when we talk about nuclear chemistry. Uranium, 2 isotopes of uranium. This is known as uranium-235 because it has a mass number of 235, and uranium-238. And here's just a pictorial representation of our hydrogen. So again, hydrogen without a neutron. And again, it doesn't need a neutron. There's no glue that needs to hold our nucleus together. And we'll kind of talk about glue and neutrons in our Next vodcast, I'm going to kind of talk about nuclear reactions. Deuterium has 1 neutron, tritium has 2. So do you understand isotopes? How many protons, neutrons, and electrons are in carbon-14? All right. So this number tells us protons. We must have 6 protons. Our neutrons are determined from our mass number, but this is always protons and neutrons, so we're going to subtract 6 from it. So we must have 8 neutrons. And because we have 6 protons, so we have 6 positively charged things, and there's no charge. Usually charge is written here on the upper right-hand side of our element. There must be 6 negative things, all right, so that our overall charge is neutral. So we must have 6 electrons. And it's going to change a little bit for carbon-11. Practice problems, we're just going to blow through that. So here's periodic table. A couple things. You need to go a couple of names of columns and just know the difference between periods and columns, or periods and families. So periods are the things that run from left to right. Okay, a period is a row. There are 7 of them. Okay, so periods are rows. And groups or families are our columns. All right. In most periodic tables, it has it split up into 18 columns. We have these at the very bottom, which really fit into the periodic table right here. The majority of these, I think pretty much most of these, are man-made. There's some exceptions, but a lot of these, unless you're a nuclear physicist, nuclear chemist, you could care less about these because we don't use them. They're all radioactive. Or I'm sorry, they're not all radioactive. This first line is not radioactive. Radioactivity begins at 83. Okay, so radioactive particles begin at 83. So these aren't, but in everyday life, even if you're a chemist, you don't deal with those. Okay, so 18 groups or families. First column is known as alkali metals. Second column, alkali earth metals. Alkali is a fancy word for base. If we put these metals in water, so lithium in water, potassium in water, sodium in water, it makes the water basic. All right. So, and same thing with our alkaline earth metals. Fluorine, chlorine, bromine, iodine, known as halogens. And then lastly, our last column are noble gases. Okay, they are all gases, and they are noble because they don't really react with anybody. Okay, kind of like think of nobility, think of Middle Ages, nobility and serfdom. And nobility was too good for the serfs, and really that's how it got its name. They were too good for the rest of our atoms. Okay, so the serfs are... We have the serfs living most of the periodic table, and then here are the kings and queens, nobility. Right? A molecule is an aggregate of 2 or more atoms in a definite arrangement held together by chemical forces. So if we have more than one atom, we have a molecule. All right, a couple of differences between these. This molecule is a molecule, but it's also an element because it has the same atom, H and H. Okay? These 3 are not elements, although they're still molecules. Okay? These 3 things are compounds. All right? So molecules can be either an element or a compound. If it's all the same element, it's an element, and if it's different atoms, or if it's the same atom, it's an element. If it's different atoms, it's a compound. Diatomic molecules contains only 2 atoms, and again, all 3 of these are diatomic elements, and then these are diatomic compounds. All right. A polyatomic molecule contains more than 2 atoms. All right. So again, several things that have more than 2. Again, this is a polyatomic molecule that is an element still, because we just have 3 oxygens, and then we have compounds once again. An ion is an atom or group of atoms that has a net positive or negative charge. How does it have this? Either gain or loss of electron. Alright? So a cation. Easy way to remember a cation, we have a T here if we kind of write it out in normal print. What does the T look like? It looks like a positive sign. So ions with a positive charge. If a neutral atom loses 1 or more electrons, it becomes a cation. Okay, so it becomes positive by losing electrons. Sodium has 11 protons, must have 11 electrons. But what happens when it becomes an ion? It loses 1 electron. Okay, so what does it have more of? It has 1 more positive thing. So it has really a positive 1 charge. Okay? An anion is something with a negative charge. If a neutral atom gains electrons, it becomes an anion. Okay, so it gains a negative charge, or it becomes negative if it gains electrons. Okay, an example of this would be chlorine. On its own has 17 protons and 17 electrons, but when it becomes an ion, it gains an electron. So what do we have more of? We have more electrons. How many more? If we just subtract, we have one more, but it's -1, so we have really a -1 charge. Okay, you can always get your charge by taking protons minus electrons. Up here, what happens when we subtract them? We have a +1. Okay. A monatomic ion contains only one atom. So these are just elements that have become ions. So sodium, calcium, aluminum ion is what we would name these. However, if it's an anion, its name changes a little bit. What happens? It gets the suffix "ide." Okay? So chlorine, instead of saying chlorine ion, we say chloride. Instead of oxygen ion, we say oxide. Instead of nitrogen ion, we say nitride. And a polyatomic ion contains more than one atom. Okay, and here's several of them. You have been tasked to memorize a bunch of these for me. You'll be having a quiz, or maybe you've already had the quiz, I can't remember. But anyways, hydroxide, cyanide, ammonium, and nitrate. Okay, so again, more than one atom, it has a charge, it will have a special name, usually ending in 8. We have a couple exceptions in here. Ammoniums are only positive. Cyanide, hydroxide, this one does have oxygen, but if it ends in O, it'll have an 8. A molecular formula shows the exact number of atoms of each element in the smallest unit of a substance. An empirical formula shows the simplest whole number ratio of atoms in a substance. Okay? So the molecular formula of water is H2O, and its empirical formula is strangely H2O, okay? Because this is a 2-to-1 ratio. Can we make that simpler whole number-wise? We cannot. Okay? If I give you the molecular formula of C6H12O6, some kind of sugar, can we reduce that empirical formula? Sure. Both are divisible by 6. So we're going to change it to CH2O, okay? Just by dividing these all by 6. And lastly, O3 is molecular formula. What's empirical formula going to be? It is O, which is kind of strange. I wouldn't even worry about that. Why is that in the PowerPoint? Oh well. N2H4. All right, we can simplify that into NH2. I think we're good. Molecular compounds. So we kind of talked a little bit about naming, just barely, with metals and nonmetals, because that is what has charges. But molecular compounds are anything that is in the upper right-hand side of the periodic table. Okay, and when we name them, so it's 2 nonmetals. Common names, we might have water, we have ammonium, or ammonia, we have methane, and then this is a buckyball, C60. All right. So we have kind of various names for things, but what should this name really be? Well, it's really dihydrogen monoxide. This is really nitrogen trihydride, carbon tetrahydride, and I have no idea what the Greek for 60 is for carbon. Oh well. But element further left on the periodic table is always written first. Alright, and the elements closest to the bottom of the group is also first. And if more than one compound can be formed from these elements, use prefixes to indicate the number of each kind of atom. And again, the last element ends in the suffix "ide." Alright, and you do need to memorize these prefixes. So just think of it as counting in Chemish. So you might know Spanish, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You might know German, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe Russian, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's pretty much my extent. But Chemish goes mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay? And really, with that, you can name any compound. The next thing is naming of acids. Alright? And acids are really oxoacids. If they have oxygens in them, there's a pretty easy way to get their name. So if we start with NO3, okay? Here's a polyatomic ion, nitrate. Okay, so it ends in 8. If we write the acid, it is just going to have an H in front of it. Okay, so H's have a positive charge, we have a -1 charge. So nitrate becomes nitric. Okay, so 8 becomes ic. If we have something like SO4 2-, this is sulfate. Okay, how many H's will it need? It will need 2 because sulfate has a -2 charge. But sulfate becomes sulfuric acid. Okay. Some things that are different. If we go to something like NO2, okay, instead of being nitrate, it's now nitrite. Okay, it's still going to get an H. It only needs one of them because of the -1 charge. But this becomes nitrous acid. Okay, so ites become us. So ates become ik, ites become us. And really our only real example up here is perchlorate, okay, ClO4. Again, HClO4, but perchlorate becomes perchloric. And likewise, hypochlorous becomes hypochlorite becomes hypochlorous acid. Okay, so ates become ik, and ites become us. An acid can be defined as a substance that yields hydrogen when dissolved in water. Okay, so any acid is going to have an H, okay, or at least for now it will. Second semester, there's maybe a couple exceptions. An oxo acid is an acid that contains hydrogen, oxygen, and some other element. Okay, so here's nitric acid, carbonic acid, and then sulfuric acid. Okay, and again, what does carbonic acid come from? It is the polyatomic ion carbonate becomes carbonic. Alright, our last slide. Or it's not our last slide, almost. A base can be defined as a substance that yields hydroxide ions when dissolved in water. And these are pretty much alkaline metals and alkaline earth for the most part. So sodium hydroxide, potassium hydroxide, barium hydroxide. And then lastly, hydrates are compounds that have a specific number of water molecules attached to them. Alright, and here's a couple examples. This is hydrated copper sulfate. Alright, so we have copper 2 sulfate. In its natural form, it's these brilliant blue crystals. And it's really this copper sulfate ionic lattice has 5 water molecules attached to every copper sulfate structure. If we heat this over a Bunsen burner, okay, or in an oven, these crystals kind of turn into this powder. And copper sulfate on its own looks like this, but this is basically the way it looks in nature. But if we heat it, drive out all the water, it turns into just a whitish powder. It kind of has a little bit of blue hint to it still. But this is a hydrate, and lots of our ionic compounds are actually hydrates. Hydrates are compounds that have a specific number of waters, and the way this works is this number just gets our chemish prefix. So barium chloride dihydrate, lithium chloride monohydrate, and magnesium sulfate heptahydrate. And that